Hello, in this video we're going to go over inner products and angles in vector spaces. Consider two vectors. I'm going to start with an example to understand the idea of inner product, why we need them, and then we'll go over the official solution, the official definition, and then we'll do some examples. So the main idea is that in order to have a geometry, you need some concepts that are geometric in nature. One of them is angle between two vectors, and the other one is length of a vector. So consider the vectors u equals x1, y1. So let's say this is the origin here, and this point is x1, y1, and this point here is x2, y2. I would like to find the relation between the angle theta and the coordinates x1, x2, y1, y2. And in fact, the relation is this. So we're going to use law of cosines to prove this relation. If you look at the distance between the points, so this is the origin, I will call that A, and this one I call that A, O, A, and B. Distance between A and B, just to remind you, law of cosine is AB squared equals OA squared plus OB squared minus 2OA times OB times cosine of the angle in between. This is the law of cosines which you learned in high school. We'll write down everything in terms of x1, x2, y1, y2. AB squared using the distance formula is x2 minus x1 squared plus y2 minus y1 squared. Distance between A and the origin, that is x1 squared plus y1 squared. Distance between B and the origin, that's x2 squared plus y2 squared minus twice. Distance between A and the origin is square root of x1 squared plus y1 squared. And distance between B and the origin is x2 squared plus y2 squared. And then we have cosine of theta. Now we're going to expand everything and then simplify. The left side is x1 squared plus x2 squared minus 2x1 x2 y2 squared plus y1 squared minus 2y1 y2 equals x1 squared plus y1 squared plus x2 squared plus y2 squared, and then minus 2 square root of x1 squared plus y1 squared square root of x2 squared plus y2 squared, and then we have cosine of theta. Now all those perfect squares cancel. x1 squared, x2 squared, y1 squared, y2 squared, they all cancel. And there's a negative 2 that cancels, so we end up with x1, x2 plus y1, y2 equals square root of x1 squared plus y1 squared times the square root of x2 squared plus y2 squared times cosine of theta. So there is a relation between the coordinates and the angle between the two vectors. So now this quantity on the left, x1, x2, y1, y2, is an important quantity, and this one is called the inner product or the dot product of the two vectors u and v that we started with. Now we can take this idea and make this more abstract. So in other words, we're going to define a function that satisfies certain properties, and then this would be one of those functions that satisfies those properties. So here is the formal definition of the inner product, and then we will do an example. The inner product or scalar product on Rn is a function that assigns a real number xy. So this is a real number that is assigned to every pair of x and y in Rn. And it satisfies these three properties. The first one is that if you take the inner product of a vector and itself, you get something positive as long as the vector is not 0. And if you go back and look at this quantity on the left, it satisfies that. If you multiply x1, y1 with x1, y1, you get x1 squared plus y1 squared, which is a non-negative quantity, and it's only 0 if x1 and y1 are both 0. This property is called positivity. The second property is symmetry. So if you do the inner product of x and y, it's the same as the inner product of y and x, because x1, x2 and x2, x1 are the same. And the last property is what we call linearity. I will go over these three properties momentarily. Note that the symmetry and linearity with respect to the first component, first vector, we can get the linearity with respect to the second vector. So let me explain that. So we know that we have linearity with respect to the first vector. So if we can also get linearity with respect to the second vector using the fact that it is symmetric. So let's do that. If you look at z inner product with ax plus by, using symmetry, we can write this down as ax plus by inner product with z. This is by symmetry. Now we're going to use linearity with respect to the first vector. So that would be a times the inner product of x and z plus b times the inner product of y and z, which is equal to, again by symmetry, xz and zx are the same, and yz and zy are also the same. So as you see, we got linearity with respect to the second vector. Okay, so let's now do an example. So we're going to do this example, which involves two different inner products. So the following functions are in fact inner products. So we have to prove three things: positivity, linearity, and symmetry. So let's start from positivity. So let's find the inner product of x1 through xn, which we don't know this is an inner product. This is just a symbol that we're using. We'll have to show that it satisfies those three properties. This is equal to the sum of xj squared, j equals 1 to n by definition. Now, this is greater than or equal to 0, since if you take any real number and square that, it's greater than or equal to 0 for all x in R. Now, I am not quite done with positivity. I need to show that this is never positive. This is never 0 if x is non-zero. If xj isn't 0 for some j, then xj squared is positive. So that tells us that when I take the inner product of x1 through xn with itself, when I apply this function, which I'm trying to show it's an inner product, this is positive if x1 through xn is in fact a non-zero vector. Okay, so what we just showed is that it satisfies positivity. Thus, the positivity is proved. So that's the first one. Now we will have to show symmetry. So we'll take the sum. So let me write it down. I'll take the inner product of x1 through xn and y1 through yn, which is the sum of xj, yj. This is equal to that by definition. But if I do the other one, if I do y1 through yn and x1 through xn, that gives me the exact same sum. That would be the sum yj xj. Now, because of the fact that addition is commutative, we get the symmetry. So since this is because addition, or I guess multiplication, because I'm doing xj, yj, and yj, xj are the same. So because multiplication is commutative. So the inner product of x1 through xn, again, this is not an inner product yet, we don't know it is, but this function applied to x1 through xn and y1 through yn is the same if I change the order of the two vectors. So this proves the symmetry. Okay, now we'll have to do the linearity. So we'll take a times x1 through xn plus b times y1 through yn, comma, z1 through zn. So this equals, first, so let me start with writing down what a, because if I'm using variables, I'll have to first start with defining them. What is x1, what is x2, what is a, what is b, etc. So let a and b be real numbers, and x1 through xn, y1 through yn, and z1 through zn be vectors in Rn. I'm going to evaluate this. This is equal to, by the way scalar multiplication in vectors work and addition works, this would be ax1 plus by1, comma, axn plus byn, and then z1 through zn. So this is equal to, so this one is by the addition and multiplication in Rn. Next, we're going to have to do the definition. So it's the sum axj plus byj times zj, j equals 1 to n. This is by definition of this function. And now I'm going to do the other one. So I will do the other side of the equality, which is a times x1 through xn, z1 through zn, and then we'll show that these two are actually the same. b times y1 through yn, z1 through zn. This is equal to, so I know by definition what the function gives us when I apply x1 through xn and z1 through zn. And what it gives us is just the sum of product of xj's and zj. So this is a times the sum of xj, zj, j equals 1 to n, plus b times the sum of yj, zj, j equals 1 to n. Now, because of the distributive law, I can write this one down as axj, zj, and then I can commute and combine like terms here. So this is j equals 1 to n, and I can factor zj. I would get axj plus byj times zj. And this, by what we found above, is exactly what we wanted. This is exactly this, which means this is the same as a x1 through xn plus b y1 through yn, comma z1 through zn. That's exactly what we wanted to show, comma z1 through zn. And this means the linearity is also being satisfied. So the function that they defined also satisfies linearity, which means it's an inner product. Okay, so the given function is an inner product. Okay, so we proved the first part of this example. Now let's look at the second part. I won't go over the details of that, but it's actually quite similar. So here's how it works. You want to show that when you multiply a vector with itself, when you do this like inner product quote unquote, we don't know if it is an inner product yet or not. We want to show this satisfies positivity. So when you do the inner product of a vector with itself, you will get x1 squared plus 2x2 squared plus 3x3 squared all the way to nxn squared. All of those squares are at least 0, and at least one of them is positive, so exact same argument. And notice that the coefficients 1, 2, 3, these coefficients are all positive. 1, 2, all the way to n. They're all positive. That's really the key. It doesn't matter that they are 1 through n. It does matter that they are positive. So therefore, the positivity is satisfied. symmetry is also pretty similar. xi, yi, and yi, xi are the same, so you have the symmetry. You also need linearity, and the linearity is also satisfied by a very similar argument. So this is also another inner product for Rn. The first inner product is an important inner product, and that's called the dot product. The first inner product of Rn in the example above is called the standard inner product of Rn, and it is sometimes called the dot product of Rn. And the definition was this. It was the sum of xj, yj, j equals 1 to n. And remember that this was the one that helped us get the angle, if you recall, up there. If I look at the very first example we did today and in this video, this guy is the standard inner product, is the dot product. And that was the one that helped us find the angle in the Euclidean geometry. So there is actually a name for that. Now, if you take a vector x or a vector v, when you take the inner product of a vector with itself with the dot product, you will get this quantity. You will get x1 squared all the way to xn squared added up, and then if you take the square root of that, that will give you the usual Euclidean distance. In R3 and R2 are the ones that we have at least seen. So in general, the length of a vector v is defined this way. If you have an inner product in a vector space in Rn, then you define the length of every vector with respect to that inner product as square root of the inner product of that vector with itself. We'll talk more about these length in another video, in a later video. Okay. Now, if you go back and look at the example that we did, we showed that u dot v with the Euclidean geometry, in the Euclidean geometry, that's length of u, length of v times cosine of the angle in between u and v. When the two vectors are orthogonal or perpendicular to each other, cosine of pi over 2 is 0. So if the angle is pi over 2, cosine of pi over 2 is 0, which means the dot product is 0. That motivates us to define this notion of orthogonality or perpendicularness in general. So we say two vectors are orthogonal if their inner product is 0. And we say vectors v1 through vn are orthogonal if and only if every pair of them are orthogonal. vi and vj are orthogonal for every I not equal to j. So let's look at an example. Show that these vectors are orthogonal using the standard inner product. So if you take 1, 3, negative 1 and dot that with negative 2, 1, 1, we will get. So if you evaluate this using the dot product, you have to multiply the first component. So 1 times negative 2 plus 3 times 1 plus negative 1 times 1. And if you add these, you get negative 2 plus 3 minus 1, which is 0. So since the dot product is 0, therefore they are orthogonal. So therefore 1, 3, negative 1 and negative 2, 1, 1 are orthogonal, but not with respect to any inner product. They are orthogonal with respect to the dot product or the standard inner product. Now watch what happens if you do this inner product with the second inner product that we had in the example. So the second inner product had some coefficients. If you evaluate that, you will get 1 times negative 2 plus so if you recall, let me actually remind you of what the inner product was. The inner product, already done on the right, inner product was the sum of I xi yi. This was the formula for the inner product. So I'll have to take 1 times the first components. So it will be 1 times negative 2 plus 2 times 3 times 1. So 2 times 3 times 1 plus 3 times negative 1 times 1. So this is equal to negative 2 plus 6 minus 3, which is 1. So this is not 0. It means these two vectors are not orthogonal. So 1, 3, negative 1 and negative 2, 1, 1 are not orthogonal relative to this new inner product. So this is the inner product that we talked about earlier in the example. So it could be that two vectors are orthogonal with respect to one inner product, but not orthogonal with respect to another inner product. It really depends on the inner product. The orthogonality is not inherent but by the vectors. It is in relation to a particular inner product. Okay, so now given the standard inner product, the dot product, we can say that the vectors e1 through en, so these are the vectors e1 through en. So e1 is 1, 0, 0, 0, 0. e2 is 0, 1, 0, 0, 0, 0. e3 is 0, 0, 1, 0, 0, 0, 0, etc. Now, we have seen that these vectors form a basis for Rn. What we also see is that if you take e1 and e2, when you do the dot product, you get 0 because there is no overlap between the ones. So all of the components are 0 except for one of the components. In the first one is in the first component. In the second one is in the second component. So that's 0. e1 dotted with e3 is also 0. So ei and ej are just 0 for every I and j that are not equal. So in other words, this is a basis of orthogonal vectors, and this is called an orthogonal basis. So what does it mean that it's an orthogonal basis? It means it is a basis which is all of the vectors are orthogonal. So let ei or n be the vector whose ith component is 1 and whose all other components are 0. Then this set e1 through en is an orthogonal basis for Rn relative to the dot product of Rn. So this is an interesting and very important basis for Rn, as you kind of have hopefully a sense of that, at least in R2 and R3. So we will talk more about this in the next video.